Hi, this is David Hodge from Montana State University, and today I'll be talking about some work we've been doing in the past few years on the topic of utilizing lignins derived from dilute acid pretreated corn stover hydrolysis residue as a phenol replacement in wood adhesives. And so you can see here some of the collaborators and graduate students and postdocs involved in some of the work here. So the background for what we'll be talking about today. We'll talk about some background on integrating biorefining with lignin utilization, and also some background on properties of lignin that might be suitable for phenol formaldehyde resins. Next, we'll talk about the behavior of lignins and hydroxycinnamic acids during dilute acid pretreatment. So this is some work that we've been doing and some experiments on basically trying to follow these hydroxycinnamic acids during pretreatments. And finally, I'll go through some work that we've done on the extraction, recovery, and characterizing properties of lignins from hydrolysis residues generated under a variety of conditions, extracted using a variety of solvents, and then go through one example of a scale-up and demonstration of recovering lignins and utilizing these as wood adhesives. All right, so now for the background. So just as background for this, phenol formaldehyde resins, they can be used as adhesives in engineered wood products. These comprise 37% of the adhesives market, which represents relatively large market, and they can be used in products that include things like plywood, oriented strand board, and laminated veneer lumber. And so challenges for utilizing lignin as a phenol replacement include its high molecular weight, its high polydispersity, and its low reactivity relative to phenol. So just highlighting what we mean by this low reactivity. So you can see here, this is phenol. So one aromatic ring for phenol can have 3 reactive sites where it can react with formaldehyde and be incorporated into the resin. Contrast that with lignin. So lignin, individual polymer with one free phenolic group as the end group may be able to have either 0 if it's a syringeal monomer, 1 site if it's a guaiacyl monomer, or 2 sites if it's an H monomer. And so that's only if it's an end group. If it's an interior group in the lignin, it has no sites because it has to be either para or ortho to the hydroxyl group. So if there's no hydroxyl group, there's no incorporation into the PF resin. And so that presents a challenge for utilizing lignins. So one of the interesting features of certain types of lignins include these acyl groups on lignins. So contrast that with lignin backbones, which have relatively low availability of free phenolic groups for integration into with these 2 ortho positions that they can be integrated into PF resins. You can contrast that with these pendant groups in grasses. That would be this parahydroxy or paracumaric acid, and in some types of woods and palms, you have acylated parahydroxy benzoate. And so both of these groups have 2 sites where they can be incorporated into PF resins. And that's one of the things that we want to do to exploit for this project is basically to take these, characterize the fate of paracumarate in grasses, follow that through pretreatment, understand its behavior during pretreatment, and then also under end recovery. So that's basically what we want to do with this work. And so just to kind of give you an idea of some of the diversity of these compounds in lignins, this is some prior work that we've done, basically trying to understand the diversity of paracumarate content in different feedstocks. So you can see here significant differences we've identified in different maize lines, within switchgrasses or other grasses. And then even within a single plant, there's enormous diversity of paracumarate contents just within individual plant anatomical fractions or as a function of plant development. So this is previous work that we've done. So another motivation for this project is our collaborator Mojgan Nishad, who's a co-author on this paper that's at Michigan State University. She's screened a number of different industrial lignins, including hardwood and softwood lignins subjected to, or that derive from kraft pulping, wheat straw, soda lignin, and hardwood and corn stover, and softwood organosolv lignins. They've compared the relative abundance of this H group in lignin, which we think is primarily derived from paracumarate. And one of the things they've identified is they have significant differences in these between the different lignins, and also they have significant differences in their performance as a wood adhesive. And you can actually correlate their performance. So this, what we're plotting here on this plot on the right, this is a dry shear stress test. Basically, this test uses the adhesive to glue two pieces of wood together and then measures the force that's required to cause this to fail. And they get the best performance out of this corn stover lignin from dilute acid pretreatment. And one of the reasons that we hypothesize this has the best performance is because of the high content of paracumarate. And that's why in this study, we want to understand the fate of this compound. And so also, one of the things that this study was able to do was, this was previously shown to act as the first drop-in replacement for 100% of the phenol without compromising product performance. And so you can see here the red line represents the conventional phenol formaldehyde resin adhesive, and this, yeah, you're within the same range. So that's and that's 100% replacement. All right, so another advantage of using this is that you can potentially tune your feedstock by selecting genotypes. So you could find high PCA content lignins by plant breeding or selecting the feedstock. You could do physical fractionation to get high PCA content lignins. And then you could also time the harvest to actually generate lignins that might be optimal for a certain application. And so what we want to do with this study is look at how lignin processing history, so how the pretreatment, how the extraction, and how the recovery and purification impact lignin properties and the recovery of the lignins and PCA content in the lignins. And so all of these, as far as we know, are unanswered questions that we hope to address with this work. So this led to this project funded by the U.S. Department of Agriculture on using, understanding the fate of PCA. So this is the scope of the project, and we're about 2.5 years, I think, into this project. So the next thing we're going to do is look at behavior of lignins and hydroxycinnamic acids during dilute acid pretreatment. So the first thing is we'll look at diverse lignins, or lignins from diverse corn stover phenotypes. Okay, so with this, we've identified that substantial PCA can be solubilized during pretreatment, and also dilute acid pretreatment at high severities results in very increasingly char-like lignins that are more difficult to recover. So that's one of the things we want to try to understand with this work. So understand the fate of PCA, understand the evolution of lignin properties during pretreatments, and determine trade-offs between obtaining high hydrolysis yields and desired lignin properties. So the first part of this study, we selected 6 corn stover genotypes from extremes and content of lignin. That's plotted on the x-axis here versus PCA content. And this is, and so 6 different genotypes that we're testing in this and trying to understand the behavior of the lignins and the PCA during these pretreatments. And then also later work, we'll use a corn stover hybrid with this lignin content and this PCA content that we'll explore. And this is published work that we published last year. So what we want to do is we tried to correlate, well, I guess the left plot here is showing glucose hydrolysis yields versus xylane solubilization. That's a generally well understood trend, is with increasing pretreatment severity, you solubilize more xylane, and one of the outcomes of the pretreatment is improved hydrolysis yields. Another thing that we've identified is the correlation between PCA content across these diverse genotypes and glucose hydrolysis yields. And you can see here the relationship that you get. And I guess what we have here is highlighted in this with this star here is we're trying to show that you can get, there are some conditions where you can get relatively high glucose hydrolysis yields or pretreatments that yield or give good hydrolysis yields following enzymatic hydrolysis simultaneously with maintaining a high content of PCA in the biomass. Okay, so the last thing is we want to look at extraction and recovery and properties of lignins recovered from hydrolysis residue. So this was understanding the impact of pretreatment conditions on PCA solubilization. This was published work from last year. So this next part, we want to look at a few different types of lignin cakes. What we want to do with this is understand the impact of the solubilization approach, so that we use a method for extracting and recovering the lignins from the lignin cake, understand the impact of that on the lignin properties. And so we're going to do a few different types of extractions: ethanol organosolv, sodium hydroxide, and formic acid organosolv extraction, and a couple different feedstocks. We're going to use an industrial lignin cake from a demonstration plant using a dilute acid pretreatment of corn stover and a number of different corn stovers that we dilute acid pretreated under different conditions in our lab. So the first thing is we'll subject the industrially generated lignin cake to a range of different extraction or conditions for ethanol organosolv extraction and sodium hydroxide extraction. And you can see here the conditions there. And then we'll subject the laboratory generated lignin cakes to sodium hydroxide and formic acid organosolv lignin extraction from the lignin cake. Okay, so this is the process that we use. All right, so this is the industrial lignin cake. And so I guess some of the features you can see from this are actually it's less than 50% lignin, has a lot of glucan, that's unhydrolyzed cellulose, and actually quite high ash content, like nearly 18% ash. And so what we're going to do is apply a number of different types of extraction approaches for recovering this. And so these can be utilized in applications. And so this is showing some of for the range of conditions for ethanol, organosolv extraction, and sodium hydroxide extraction. And so I guess the take homes from this are, at least for the condition for this lignin cake and for the conditions that we tested, the sodium hydroxide extraction was much more effective at solubilizing, well, especially at the high temperatures, much more effective at solubilizing lignin and recovering lignin from these lignin cakes. However, the downside of this is, so you can see this orange bar here represents the PCA content in the original lignin cake. You can see here that the ethanol organosolv preserves this PCA ester much more effectively than the NaOH extraction. So that's the downside of this. So you can get higher yields, but you have lower PCA content. So the next thing that we did was we looked at, and we've done other things with that study as well, but this was just some of the highlights. So the other thing that we did was looked at the impact of pretreatment severity on lignin extractability and properties. So this one, we subjected a hybrid corn stover to a range of different pretreatment conditions, dilute acid pretreatment conditions, and then looked at the solubility or extractability of the resulting lignin. And so I guess the highlight from this, on the right side, you can see this is, I guess, actually different combined severity factors, but yeah, actually, there were a lot of things changing at the same time, initial pH, and the temperature that we tested these at. So most of these were at 150, and this extremely severe condition was at 200. We just wanted one extreme condition. That resulted in very, very poor extractability of the lignins, I think, because these were much more char-like. But you can see here, both the formic acid extraction and the NaOH extraction resulted in like between 60% and 75% lignin yields. And one of the interesting things from this, and we also characterized a number of properties, including molecular weight. One of the interesting things from this was, if you look at this plot on the right, you can see that the PCA content in the unextracted, you have significant differences between the pretreatment conditions in the amount of PCA that's left in the lignin after the pretreatment. However, when you do the extractions, again, like the ethanol versus the NOH for the industrial lignin cake. You can see here the formic acid is relatively good at both, from this previous slide, both at recovering high yields of lignin and relative to the NaOH, and good at preserving the PCA. So what we did with this was we selected one of these conditions for scale up and then testing the properties of the PF resin. And so this was the condition that we tested. And so what we did next was scaled up from about 5 grams to more than 500 grams in this RegMed digester. Actually, this digester was manufactured in Sao Paulo, Brazil. We did the extraction in formic acid, and then we used these, I guess our collaborator at Michigan State, Moshgan Nishad, used these lignins and tested some of the properties as an adhesive. And so many other properties of the resin and the adhesive were tested. We're just going to be showing one type of property, this dry shear strength. And so one of the things that you can see from this is that we have, relative to the conventional PF resin, and we can generate lignins, both the commercial from the commercial lignin cake. This was published in previous work, and in the current work using the formic acid extraction, we can generate lignins or resins and adhesives with properties comparable to conventional PF resin with 100% replacement of phenol with these lignins. And one of the things that we did was we developed an improved extraction approach where we get higher extraction yields, improved lignin properties, and then also improved resin and adhesive properties. We won't talk about the details of that, but you can also compare this with some of the other lignins that were tested in prior work, so superior performance to those. So just to highlight what we did, paracumarate is a key structural component of grass lignins that we hypothesize is responsible for improved resin performance. The ester bond is labile during pretreatments, and we developed a better understanding of how these things process during pretreatments. And we tried to find a balance between pretreatment conditions for high sugar yields versus PCA content and extraction conditions that yielded high recovery yields and high PCA contents. And we demonstrated that we can utilize these in PF resins. So with that, I'd like to thank you for your attention. And these are some of the students from my lab who are involved in this work. And I guess with that, I can take questions.
Hello, everyone. I am Fabio Squina, and the title of my presentation is From Renewable to Value-Added Products, Applying Discovery-Based Omics of Natural Ligninolytic Systems. As you can see in this first slide, agricultural and forest residues are abundant and a low-cost source of chemical compounds and molecules with high energy. And plant biomass conversion technologies are a central player in all biorefinery initiatives, which are aimed to replace fossil fuel to produce chemical fuel and materials. The transition from a fossil fuel economy to a more sustainable bioeconomy is important not only because of environmental and climate change issues, but this transition is important because these actions, these novel technologies based on biomass conversion strategies, these technologies can stimulate job growth and promote economical opportunities. However, the sacrification of plant cell wall is a complicated and lengthy process, mainly due to the inherent recalcitrance and complex heterogeneity of the polymers that comprise plant cell wall. During the past 10 years, we have studied different natural ligninocellulolytic systems. Some of them are shown in this graph. Natural systems that are capable to efficiently utilize plant biomass material as source of nutrition. And our hypothesis is that by understanding the biomass conversion in this nature utilization system, we expect that these studies help us to develop biocatalytic strategies and harness the potential of converting plant biomass on chemicals and commodities. After this short introduction, now I show the main topics of my presentation. Today I will tell some of our experience on studying the biocatalytic degradation system of the termite, which we call as digestomics, and how we apply this knowledge to biomass, to bioproducts applications. This study was mainly done by João Paulo Cairo, who is a postdoc of my group. The termites are the smallest and the most efficient bioreactor that decomposes lignocellulose on Earth. It's a very small compartment and very efficient. And as you can see in this graph, there is a drastic variation of pH, partial pressure of O2 and H2 among these gut compartments. What is more interesting about this system is that it kind of resembles what we would expect for a biorefinery contest. The termite has a powerful mandible, which reduces the lignocellulose material up to about 20 micrometers. After the action of the mandible, the material is directed to another structure called gizzard, which further reduce this material. And in the two initial compartments of the termite gut, the foregut and the midgut, endogenous enzymes are secreted. Glycoside hydrolases, lacases, esterases, endogenous enzymes are found to be secreted in this initial compartment of the termite gut. Then the digestive material is directed to the hindgut, which is populated by microorganisms, symbiotic microorganisms. These microorganisms utilize this digestive material, and this metabolism results on fermentation products, which are the main source of the nutrition of the termite. And so the termites really resemble what we would expect to a biorefinery, a plant biomass refinery, how it would operate with a physical, biochemical, and fermentative process occurring in a connected way. We started to study the biocatalytic system of the termite about 10 years ago. We chose the Coptothermus destroy, which is a major pest in the state of São Paulo, as model organism for these studies. So we cloned the two major cellulases produced by this termite, Coptothermus destroy, an aminoglucanase, EG1, and a beta-glucanase, BG1. And we found that when these two enzymes are combined, they present a high synergy. So they have, when combining, these two enzymes has a synergistic effect on degrading cellulose. And what is interesting is that another interesting point about the termite biocatalytic system is that the termite do not produce cellulobiohydrolases, which are found to be a major player on fungal cellulolytic systems. So these insights brought us a hypothesis whether the termite could have chosen a different evolution path because it does not produce a major player on cellulose degradation, the cellulobiohydrolases. And we did a comprehensive structural and biochemical characterization of the two major cellulases produced by the termite. And this first study, the result of this first study was kind of disappointing because what we found was that these two enzymes are not so efficient to explain all the capability of the termites to degrade lignocellulose, because the two enzymes together, the performance of these two enzymes together are much significantly worse when compared to fungal cellulolytic systems. And this study raised a question whether the termite could perform other enzymatic mechanisms for biomass degradation. And we did omics analysis of this termite. We submitted the animal to different feeding treatments. And these studies revealed the presence of SOD, a superoxidase mutase, which was upregulated on the transcriptomic analysis and proteomic analysis, indicating that this enzyme is important for degradation of material of high recalcitrance, such as sugarcane bagasse. We cloned this superoxidase mutase from Corptoterms destroy. We did immunolocalization studies. It is located and produced in the initial compartments of the termite gut, as well as the endoglucanase also is produced in the initial part of the termite gut. So the superoxidase mutase is sharing the same compartment where this endoglucanase is produced. And we did biochemical studies combining the endoglucanase and the superoxidase mutase. And we found when these two enzymes are combined, we could appreciate a synergistic effect on cellulose degradation. And we also observed that this superoxidase mutase, we also observed that the superoxidase mutase activity can release oxidized oligosaccharides by this enzymatic mechanism. So that's the typical superoxidase mutase activity. We would expect that enzyme would release, typical superoxidase mutase would release hydrogen peroxide. But to explain this activity on cellulose polymers, we would expect that the enzyme be able to produce hydrogen peroxide. And actually, a study from the 1990s showed that, in fact, superoxidase mutase can catalyze the production of hydrogen peroxide. And our enzyme also was able to produce hydrogen peroxide. And we mapped the oligos produced by the superoxidase mutase enzymatic activity. And we, after mapping these ion products, we found that the oligos produced, the oxidized oligos produced by the enzyme action was compatible with hydroxyl radical attack. So the conclusion of this work is that this superoxidase mutase from Corptoterms destroy can oxidatively modify the substrates and improve the access to other glycoside hydrolase, and explain this, and this would explain that synergistic effect that we saw on the biochemical assays. This model of operation is very similar to what is found to lytic polysaccharide monooxygenase, LPMOs. And these studies resulted on a patent application. The utilization of this SOD enzymatic preparation as an additive to caseine mixture applied for on second generation ethanol production or other added products. And finally, I'm going to go very briefly on the second part because I'm running out of time. This work was led by Robson Tramontina, who is a a PG study, a PG student of my group. And it's about another enzyme based on our Omics analysis. The capital terms destroy aldocato reductase. Also, the enzyme is produced in the initial compartment of the gut of the termite. The same that we saw before for the SOD and also from the endoglutenase. We solved the three-dimensional structure of the enzyme, and we found that this aldocato reductase can act on different aromatic and aliphatic aldehydes. And we found a potential application of the enzyme to produce coniferol. Coniferol is the building block that can be used for the production of other bioactive compounds, also fragrance compounds. And we decided to apply this aldocato reductase to produce coniferol, but we would need another enzyme, a carboxylic acid reductase. And we combined our aldocato reductase with several carboxylic acid reductase, and we found this carboxylic acid reductase from Nocardia that was very efficient in vitro to produce coniferol as end product. We cloned and expressed these two enzymes in E. coli, and this in vivo system was very efficient to convert ferulic acid on coniferol, as you can see in this graph. And the next step was to apply this technology into a real material, in a real lignocellulosic material. And combining with other enzymes described by our study, the Shinzi from Clostridium thermocellum, we developed a system, a one-pot system to produce coniferol from lignocellulosic materials such as wheat straw and also wheat arabinoxylon. Unfortunately, I had to pass very rapid this second part of my presentation. So I invite you all to read our previous manuscripts describing this aldocato reductase as a multi-purpose enzyme for biorefinery applications. There are a lot of people to say thanks, a lot of people that helped, and without them, this work won't happen. And I also would like to appreciate FAPESP and CNPq for the funding. Have a good day.
Hi, my name is Andrea Cressoni de Conti. I'm from São Paulo University State Unesp campus of Rosanna, and I am a leader of the research group called Biofuels. The study that I'm going to talk here is about the use of the raw cassava rhizome waste as a binder in the sugarcane bagasse and straw briquettes. This study was developed with the researchers Marcos Paula Pata Granada, Elias Ricardo Duranque Padilho, Gabriela Tami Nakashima, Cláudio de Conti, Fabio Minoria Maggi, and me. We receive financial support by FAPESP and CAPES. As we know, the economic development of a country is linked with the energy consumption and so the industrialization. Brazil has a lot of biomass from agriculture like sugarcane bagasse, sugarcane straw, and cassava rhizome. These residues have a low density and we can increase this make a process called energy densification. We can see this process in briquettes. In the literature, we found studies with sugarcane bagasse and sugarcane straw briquettes, and in this study, it was used the cassava stalk like a binder. The aim of this study is to evaluate the raw cassava rhizome like a binder. We made the mixtures of the raw cassava with the other residues. We verified the properties of the briquettes made with these mixtures. So, materials and method. To analyze this, we used the following materials and methodology. The material that we used were cassava rhizome, sugarcane bagasse, and sugarcane straw. Methods. To try the materials, we use ASTM D3173. We analyzed the particle size distribution with SANS trace TS 1549-32. After analyzing distribution, we take the particle that passed through of the aperture 20 mesh and remained in the aperture 40 mesh. With the sieved materials, we made 6 blends, where 3 are mixture of the materials. They are B1, B2, and B3, and the other 3 are with 100% of the materials. So we have B4, B5, and B6. We can see the blends in the table 1. Approximate analysis and high heating value. For approximate analysis and high heating value, we use ASTM D31373, ASTM D3175 standard respectively, and to calculate the fixed carbon, we used equation 1. To analyze the high heating value, it was performed using a calorimeter based on ASTM D2015 trace 96. Bulk density. To study the bulk density, we use the ASTM E873 trace 13, and the calculus is given in equation 2. Apparent density. Apparent density was calculated by equation 3. This density gives the density of the briquette and depends on the mass and the volume of it. Energy apparent density. The energy apparent density gives the energy that has in the briquette, and it was calculated with equation 4. This energy apparent depends on the apparent density and high heat value. Energy bulk density. Energy bulk density was calculated with equation 5 and depends on bulk density and high heat value. Energy comparison index. We also use the energy comparison index given in equation 6. This index gives us how much the energy increased in briquette process when we compare the energy that has in briquette with the energy that has in raw material. Briquettes volumetric expansion and physics tests. To make the briquettes, we use a lab scale press model LB32. After made the briquettes, we determined the volumetric expansion measuring the volume with the briquette with a digital pachymeter in 1, 3, 5, 7, 24, 48, and 72 hours. And finally, we calculate the volumetric expansion with equation 8. Resistance to compression. We analyze the resistance to compression using the standard NBR 7222-2011. With this test, we can calculate the maximum stacking height, equation 10, and the number of samples stacked, equation 9. Durability. The durability test was performed with SANS trace TS 1520-2. We used a roller drum KT3010 and we calculated the durability with equation 11. Scan electron microscopy and energy dispersive spectroscopy. We also passed the ash material in scan electron microscopy and energy dispersive spectroscopy. We used a novel and tuck test to analyze the data with 95% confidence. Results and discussion. Analyzing the density, we can saw that we obtain higher apparent density than the literature. The high comparison index was 2 B4, that is composed by 100% sugarcane bagasse, and for blended the higher index was 2 B1. Volumetric expansion. For volumetric expansion, we see in figure that after 72 hours the brick tends to stabilize. And in table 3, you see that the higher expansion occurred to B5, that is composite only sugarcane straw. The lower expansion occurred to B6, that is composite only cassava rhizome residue. To the blends, we can see that the 3 blends B1, B2, B3 show a similar behavior. Compression test. To compression test, when we compare with the literature, we saw we obtain values for fracture limit, ultimate strength, and maximum stacking rate higher than we found in Da Silva 2050. To 100% material, you obtain that blend 6 presents the higher values. For the blends, we saw that B2 presents the better result. When we compare with B4 and B5, it can see that the values increase B2 in 39% when we compare B4 and 135% when we compare with B5. Proximate analysis and high heating value. In proximate analysis, we can find a lower volatility content value to B6 when we compare with this literature. You can explain by the fact that we didn't wash in the rest. For B1, B2, and B3, we saw that the values are similar. To ash content, we saw that B6 presents 3.1 times the ash content that we found in the literature. Here again, we explain by the fact that we didn't wash in the rest. For the fixed carbon, we saw that B4 presented the lower value, and this is because this blend presents high volatility content and high ash content. The higher value for fixed carbon was obtained to B6 that was made only 100% with cassava rhizome. It showed that this briquette will be more resilient during the combustion process. For high heat value, we found a lower value when we compare the literature, and this happened because we didn't wash the residue. So, watching all the results, we infer that the best composition happens with blend B2 because we saw good high heat value, good fixed carbon content, low ash content, and good volatility content. Durability. In the literature, it showed that the good values to durability is in 90%. So the results of the durability show that all the composition briquettes present here show good values, and so these values guarantee the mechanical resistance of briquettes during transport and handling. When we look at the scanning electron microscope and energy dispersive spectroscope, we saw that B1, B2, B3, and B6 having a high calcium and potassium, and B1, B4, and B5 presented high silica. Conclusion. With this study, we can conclude raw cassava rhizomes can be used as natural binders in the formation of briquettes from mixture of bagasse and sugarcane straw. The use of 75% raw cassava rhizome in B2 produce briquettes 39% more resistant than briquettes of pure bagasse and 135% more resistant than pure straw briquettes. Energy densification in the briquette of bagasse, sugarcane straw, and cassava rhizome was 6.4 to 6.7 times greater than the energy density in the natural material. All the briquettes present excellent durability, 97%. The blends B1, B2, and B3 can be used for briquette production according to the availability of the materials. I want to acknowledge FAPESP and CAPES for financially supporting our study. Here is the principal reference that we use in this presentation. So, thank you.
I'm Adilson Gonçalves from the Bioenergy Research Institute, IPBEM, at Unesp in Rio Claro, São Paulo State, Brazil. First of all, I'd like to thank the BBEST for this virtual conference and for giving me the opportunity to share with you some initial results that we have on lignins converted to valuable materials in biorefinery concept. That's very special in function of the current days in these pandemic days. So, first of all, that's clear for us that the fossil-based energy and materials, petroleum, oil, coal, produces mainly fuels and energy, and a part of this material is used for the chemical industries. In comparison with the biomass-based industry or the biorefinery, we have more 50 to 50 separation for the energy and chemical industry utilization. The main reason here is the oxygen content. We have less oxygen content in oil, then we can use it better for energy, and more energy and we have more oxygen content in biomass. That's better to be used for chemical industry. Remember, when we have oil, petrol, we need to functionalize this material to be used, and biomass is still functionalized. On the other hand, biomass has a higher heterogeneity. That's a barrier for this complete utilization. Based on this concept, we are working mainly on lignin utilization. In this figure, that's very simple. We just compared making a search on the internet, how many entries we have for lignin and cellulose, using even Portuguese, English, and German words. Comparing cellulose and lignin, we have more entries for cellulose, of course, than for lignin. But this is situation comparing Google, Cielo, that's a Brazilian based, and Web of Knowledge, divided between articles and patents. You can maintain these red numbers for patents. We have more cellulose than lignin. Okay, but when we make this division comparing lignin to cellulose, of course we have 2 to 6 times more cellulose citations in comparison with lignin. Okay, seeing that the research is more, cellulose is more interesting to be studied. When we compare lignin to cellulose, 2 to 6 times more citations of cellulose in comparison with the lignin. You look into articles and texts, but the patent numbers has the twice this value. That means we are interested on cellulose, of course, but we have less technical application for the lignin. So then we need to study more this lignin. And then there's a very interesting challenge. There's opportunity to be evaluated, the utilization of lignin. So one of the problems is the structure and characterization of this lignin. We need to remember most of the lignin used at the moment is from this second generation ethanol, using mainly grass materials. Then we have another nature of this lignin that must be evaluated, for example, through analytical pyrolysis, chromatographic, and spectroscopical analysis. So this heterogeneity is then the first product to be evaluated. That's the first product we have as to be evaluated. So that's also a contribution to cellulose recalcitrance in respect to this second generation ethanol production. Then we need to evaluate contact with cellulose, reagent consumption, and other characterizations. So in this aspect, we started at IPBEM a joint project founded by FAPESP. The name is Fructo Refinery. And for us, the banana residues are the main raw materials to be evaluated. We analyzed the extraction of this lignin, for example, by organosolve, hydrothermal pretreatment, and also NaOH solubilization. So the first question is a rapid method to make this question answered. What is the best combination of extraction and utilization for this lignin or these lignins obtained from banana residues? And also the social impacts will be evaluated in future, not in this paper. The first question here is the analysis of total carbohydrate and lignin contents, because at this moment we still did not have HPLC working. Today we have, but at this moment we needed to find other methods to make this evaluation. So the first one was the traditional DNS reducting sugars, and then here we have this evaluated. We can make that in different pH, but the pH 1, that's the pH when we obtain it after this sulfuric acid, the Clason method hydrolysis, then you can make this measured as we can see here in this blue bar, okay? So together with that, we studied the solubilization of lignin, but not just the craft lignin that's used, but also the Clason lignin. That's this lignin used mainly just to make as mass balance to evaluate the amount of lignin. And here we can see the craft lignin can be solubilized in dioxane solutions over 90%. When we move to Clason lignin, we can reach more than 50% of its solubilization, changing this combination, changing this percentage of dioxane in this aqueous solution. So that was just one result we obtained at starting this study. So moving to the utilization of the lignin, the first parameters evaluated was the controlled release of some substance mixed with lignin, and lignin here used as a matrix for this controlled release formulation. So here we can see some aspects of the lignin putting together in a diffusion of this lignin when we have this dark aspect of this mixture, and then put in water to make the solution. Here we can see that some of this release was measured within the time, and this is a normal situation for this Fick's law, the first derivative of the Fick's law, and that is a modeling for this release. And we are studying at the moment the change of this release towards different lignin nature. That means we can use other lignins or then make some derivative of this lignin. So the second one was the oxidation of this lignin. You can see here some representative an illustration of this lignin with more oxygen groups, and then making the chelations to metals, in this case, copper as an example of this. So we have started this oxidation using kinetic parameters evaluated by the oxidation of permanganate over lignin and measured by UV absorption. Then we make these in different times to have these parameters, also kinetics and even the activation energy, making within different temperatures. So the first result here is that the kinetic together with copper addition, we can see a more chelating capacity of this oxidized lignin in main 20% of more metals that are removed by this oxidized lignin. Remember that this chelation here is used as a parameter, but the material can be used even for agrochemical delivery or even for the wastewater treatment for the removal of some metal. Last example we have that's the photoprotection of dyes using lignin. In this case, we used different dyes together with lignin, putting this mixture under a UV lamp to make some simulations of the degradation. In this graphic, we have an example for brown dye. In mixture with lignin, we can see a 5% photoprotection of this dye. Is an initial result. We are starting to make this more deeply using intemperance chamber to evaluate these protections along the time. As a final remarks, we can see then the oxidation, chelation, control release rate, and percentage of photoprotections are to be used as parameters to evaluate the best conversion routes to extract lignin and its utilization. The results are the experiments here related are not just only the utilization of the lignin, but they are intended to be applied to this data using modeling mathematics to make that. So, and the rapid carbohydrates and lignin quantifications was very important when we didn't have some normal chromatography analysis to make this evaluation. That's very important to see that we can see some of these ground data with simple and rapid methods. So finally, the acknowledgements to FAPESP for the founding of this project and CAPES and CNPq for giving us fellowships for the students. Special thanks to Dr. Igor Polikarpov for University of São Paulo and Dr. Thelma Franco from Unicamp. They still believe in my work. Thank you very much. Thank you for the attention and having in mind that Brazil is better than the government we have at this moment. Thank you.